Okay, just to summarize, Eric, if you're watching this, we just went over this and we stated here that we have a latent phase and we have a sensible phase. And just to bring it back to the psychometric chart, we went from 80% relative humidity and 20 degrees, so about here, and we moved across here. So we're definitely in the sensible here. And then we dropped it from here down to 5 degrees C, and this is latent heat that we are removing. And if we come to the engineering toolbox, and if you put in engineering toolbox and latent heat flow, what comes out is, I like the metric version because that's what we're dealing with. Latent heat flow equals that latent heat of vaporization of water, the density of air, the airflow in meters cubed per hour, and the humidity ratio. Which, if we go back to yesterday in those spreadsheets, that was thermal inventory, and we have our latent heat tab, and it's asking us for temperature high, relative humidity high, and T low and relative humidity low. And what comes out here is these H's and the grams per kilogram. So those two represent, and those are automatically interpolated from this data here. So you put these two numbers in here, and it goes and it just knows, it looks at the psychometric chart. So you put in your temperature and your relative humidity. So in our case, it would be 20 and 80. And we come across over here, and here is that humidity ratio piece. And we're looking at about 0.012 approximately. So which coincides with our, oh yeah, I got to put in the temperature. So we said 20 degrees and 80% and 11.7. Now that's grams, so that's, just multiply by 1,000. I said 0.012. Theirs is a little more accurate. They've got 0.0117. Okay. And then our temperature low was 5 and relative humidity was 100. And that comes out, back to the psychometric chart, 5 degrees C and 100% relative humidity, so about 0.0051 or 2 over here on this side. And yeah, so 0.0054 was the interpolated data that they got.
Do that one more time?
Yeah, sure. Okay, so you've got your psychometric chart.
Yeah.
Okay. So it's 5 degrees C and 100% relative humidity.
Yeah.
What is the humidity ratio?
It's like 0.006 or something?
Yep, I got about 0.0055 or 6. Yeah, in that ballpark.
Okay.
Yep. Xavier, you good on that? Matt?
Yeah.
Nick?
Are you just going for the 100 on the curve diagonally to?
Yeah, so you got 5 degrees C here and 100% relative humidity, so that's that red line. We're on the dew point, and then you kind of just you can see the blue line is 0.005, so you're just above that blue line over here on this right-hand chart. So you just want to go here to the 5, right where my cursor is now, and then follow it over to this side.
Are you going from the 100% that's along that curve?
Yeah, we got 100 here, 90, 80.
Okay. So
70?
You go from that 100 diagonally down?
Well, you follow the curve. Yes.
Okay.
Yeah.
Okay.
Okay, so I know how to find that number, but can we just maybe talk about what that, exactly that number is? Humidity ratio, so,
It's grams of water per gram of dry air.
grams
What's
of
the humidity content? Water content?
Yeah, it's like how much water versus how much air. It's a ratio. And we can expect, right? We are in this case we talked about yesterday. We're dehumidifying, so we're taking water out. So we can expect that our humidity ratio, our grams of water per grams of dry air, would that go up or down?
yeah.
Down, right? We've gone from up here, 20 and 80. So we were at, I think we said, what did we say? Okay, so what is it at 20 and 80? So 20 degrees C.
It's like 0.12 maybe?
Yeah, about 0.12. 0.012.
Yeah, yeah, yeah.
Yeah. Okay.
So, okay, here's the part I'm having a hard time wrapping my head around. We're at 100% humidity at like 17 degrees, right?
Yeah.
Then we drop the temperature down, and we're still to 5 degrees, but we're still at 100% humidity.
Yes.
But the ratio of water to dry air. So even though we're at 100% humidity at the beginning and the end, we have lost water, but we remain at 100% humidity. Am I looking at that
Yes.
wrong?
Yep. Yeah. Exactly. And picture, picture this heat pump. It doesn't have that heating coil like we talked about on the board yesterday. It doesn't have that heating coil afterwards. And this goes back to air conditioning fundamentals. If you want to do air conditioning and dehumidification, the air conditioner needs to run long enough that condensation starts to form and we remove moisture.
So that's why it's latent then, because we're staying at 100% humidity.
It's latent because we're removing moisture, and moisture is a consideration, but
Right.
mainly because we're taking moisture out of the air.
Like I just thought if it's something saturated, it's 100% humidity, then as soon as you start to drop the temperature, it would,
Well, as you drop the
That-
temperature, water
I
leaves
guess-
it.
right, yeah.
As water leaves it, the temperature drops at the same time. They just kind of follow each other.
Okay, I can dig it.
Okay, and like I said, you'll hear cases where if the air conditioning system is oversized, it will drop the temperature really quick, but it won't do any dehumidification. And I don't know the exact principles of that. I've heard that at least 10 times. You need to properly. It's actually in the Green Building book. It talks about it. If you can't, it's not like a heating system. You have to size it properly so that it runs long enough so that you remove moisture from the air. Because it does take time for that condensation to form and take it out of the air.
So yeah, so then we start to heat the air up again.
We start to heat the air up again, yep. And does the humidity ratio change when we're heating the air up?
No.
No. And no moisture's being added, no moisture's being taken out, and that's why we are in the sensible range.
Because the humidity's not changing.
Because the humidity ratio is not changing. If you look at this,
The humidity's changing, but the ratio isn't.
the relative humidity is changing,
Right.
but the humidity ratio is not.
Right.
Okay, if we look at this, again, go back to the engineering toolbox, the latent heat flow can be expressed as this. So we've got H, which is a constant, the latent heat of vaporization of water. The density of air is a constant, at relative conditions, as long as the pressure and temperatures aren't crazy. The airflow is a given. What matters here in a latent heat flow is this delta X, the change in humidity ratio. So if we go back and look at the psychometric chart, we're moving straight across, our humidity ratio doesn't change, so it would be a 0 change there for latent heat. Okay, but thankfully, if we look at this, we also have airflow sensible on this.
That just doesn't factor in humidity at all.
No, it doesn't factor in humidity at all.
Right.
Okay, but you can, we know that at a higher temperature, it can hold more moisture. So the relative humidity is, you know, this relative humidity is going to be lower than this relative humidity. But it's that old formula, Q equals CFM 1.08 times 1.08 CFM times delta T. That's what this formula is. The sensible flow, and this is what we used last year when we were doing all that ductwork stuff. But when we get into dehumidification or air conditioning, we need to factor in that latent heat piece. Okay, so I'd like everybody just to go on and get this page up on your computers if you're logged in, because this is the formula that you're going to want. Or actually, I guess you can just use this page here.
What did you ask us to do? Open latent heat?
Um,
Or no?
if you want, you can do this engineering toolbox and you can get this formula. But at the same time I'm saying this, if we look at this formula and we come across here to this number here, so it's I just kind of wanted to prove that this formula here that's here is this formula. Okay, but let's go through this and we'll put in the Carey dehumidification system here. So we said 5,000 CFM, which was $2360 liters per second. 2360. Okay. I'm gonna.
Question. Oh, no, never mind.
Okay. So what was our? I'm gonna try this two different ways. I want to see if we come up with the same answer or not. So I would like to do one that coincides with, you know, going from here to here on the latent phase, and then plus the 20 to 80% relative humidity on the sensible phase. And I'd also like to do this one just in the latent phase to see if they line up or if they don't. And so we would need to factor that in.
That's what I was wondering.
And if I look at this, I'm thinking that they should be. You should have to do 100% to 5%. It's kind of like you're taking a shortcut if you go from here to here. But let's find out. So the difference was temperature high
17.
80.
Or
Yeah, that's the question mark, right? It's yeah, I'd say about 17.
16 and a half.
Yeah. Okay, let's go 16.5. Relative humidity be 100. T low is 5.
No, it just goes to 17.
Yeah, but it is actually 16.5 if you look.
Oh, it's calculating it at 16.5.
Yeah. Okay, so this is we'll put at 17.5.
16.
Oh yeah, sorry.
Which document is this?
This is thermal inventory on the spreadsheets. So if you go on the presentations yesterday, number 9, and then there's a link to these documents again. And I am recording this, so if you need to go back, you can. Hopefully that's working. Yeah, we're recording. And then we also have Carry dehumid 20 to 5. So 2360, 20, 100, 500. Okay, so right now there is a difference of, between those two, there's a difference of almost 20 kilowatts.
That's a lot.
Yeah. So let's go see what the sensible load would be from 16.5. This would be 20. This is 16.5. And this was 2630 or
2360.
2360. 10.2. %, LH, and
Hold on a minute. Can you go back to your other one? There's latent.
yep.
You need to change the humidity. It's 80%.
Oh yes, thank you.
And that will solve the problem.
Change them above it too?
No. No.
Oh, right now it's on.
I don't know if it solves the problem, but it's
If yeah, I'm wrong somewhere.
well. No, I don't. You get the same result, really.
Yeah, there's not much difference.
Okay, you can say that's the same result.
It's very minor here, but it's 10 kilowatts.
Yeah, but I don't think. How can that be sensible if we're not factoring in humidity? I think that's the difference. This is just, the sensible heat is saying it's staying at whatever, the same humidity.
Yeah, so this here assumes air at about 50% RH and 21 degrees C. Yeah, so it doesn't go from, it's not at 50% RH for starters, it's at 100%.
Yeah. Well, no, it's 80%.
Yeah, So let's just go with this one because this actually makes the most sense because we're going. This is what we're actually doing. We're going from this 20%, 20 degrees C,
Yeah.
80% relative humidity, and 5 and 100. And we could say the same thing for the carry heat side. 5 to 20. And so it's about 40% RH and 5.
2.8.
Okay. So we'll just delete that.
Yeah, so you can fill that out just by exactly following
This.
the psychometric chart, the
Yeah.
lines on your psychometric chart.
Yeah.
So what's the deal that sensible heat doesn't apply to this? Is it already calculated in or?
The problem with this sensible side is that it's at about 50% RH and 21 degrees C. So they're using constants here when realistically, in this scenario, we're going from 40 or 100% RH to 40% RH. So our relative humidity is changing too much to be able to use this sensible portion. Okay, let's change gears here and look at the final.
Still a little bit confused.
I thought I had this completely squared away, but obviously I don't.
Like if you look at the bottom of the latent heat, it says the calculation assumes conditions for which the constant is 3 joules per liter.
Where do you see that?
At the bottom of the latent heat. Yeah, right there. So, but that would change based on the humidity. So how is it a constant? Whereas the other one at 50% humidity, the constant is.
Well, what is that joules per liter is, if you look at the, it's that latent heat of it's these two numbers combined, your H and your delta, or not delta, your density.
Okay. But why is it then on the sensible 1.23 joules per liter? Per liter degrees C.
I'm gonna regroup here. I'm gonna pull back on this because I obviously am not squared away yet, and I want to move ahead with the midterm,
Okay.
or sorry, final. I should change this to final, and just make sure everybody's good to go. And what we'll do is cross out the B, 2B. So cross out 2B. But I just want to go through this and make sure everybody's understands everything I'm asking, and that we're all good to go on it. Okay, so the first part is the Cass Building is a Maritime Electric customer in the general service category. Has a peak demand of 110 kilowatts and monthly consumption of 68,000 kilowatt hours. Okay, so you'll have to go on the Maritime Electric website, find the general service category, and then tell me, question 1, if 1 kilowatt of electrical demand is saved per month, how much money will Holland College save? What will you have to factor in on top of what's listed on the site? There's with an H.
Heating degree days?
S
T.
T.
Oh, I just did.
Yeah. Okay, same thing for the next one. So 1 kilowatt of electrical demand, that should say, glad we're doing this, going this over. So electrical consumption instead of demand for 1B. Everybody see that?
Yeah, so you just wanna make sure we factor in the taxes.
Yeah, just I'm kind of, instead of just putting it all down in text and going through it kind of step by step
Yeah.
for you folks, okay? Okay, here's where I said people are going to get different numbers and different light bulbs. So if we recommend to replace the lights in blank, this is where everybody's going to have a different value here, with blank watt LEDs, how much money in lighting energy will be saved? So assume the following. Heating and cooling costs will be considered in follow-on questions. Lights are on 8 hours per day, 5 days per week, all year. And the lights contribute to peak demand.
Wait, hold up. So you were saying that don't have to look at heating and cooling at this
I
point?
said you will in follow-on questions.
Well, I know for number C.
Number C, you do not have to factor in heating and cooling.
Okay.
Okay?
Now, the blanks, you're just picking a room?
Yes.
Do you need, and you want us to know exactly how many lights are in that room?
Yeah, I'm going to assign that once you're comfortable with this. I'll tell you
Okay.
what room you're going to get.
One more question.
Yep.
Yesterday Nick made a good point about the lumens, but we're not gonna factor that in?
No.
Like, okay,
No, we won't factor that in.
so we're just going equivalent wattage,
Yeah. Yep.
okay?
So if this is a 32 watt T8, what will you have to factor in?
The balance.
The ballast.
Yeah.
Good. Any questions? Any other questions on C? Question D. Supplemental heating. When we install lower wattage lights, we will have to provide more heating from the geothermal system. The heating system operates approximately blank months per year at a COP of blank. So again, you'll get different values there.
I see what you do.
How much additional kilowatts and kilowatt hours will be required to make up that additional heat required? Okay, and additional kilowatts is kind of the fuzzy one, I think, in that scenario. Okay, so assume, if you had 3 kilowatts of lighting demand and you had a COP of 3, assume 1 kilowatt of extra demand. So the demand and the kilowatts are proportional to the COP. Follow me on that, Xavier? Yeah? Okay.
You say 3 kilowatt and then you got a COP of 3?
Yeah, like if we calculated in this room, we had 3 kilowatts of lighting. So we're gonna, we had 3 kilowatts of lighting that we're gonna save. That's our savings. And now our heat pump needs to make that up, right? It needs to make up that 3 kilowatts. So assume that if the COP of the heating system is 3, then assume it takes 1 kilowatt from the heat pump to make it up.
To make up 1 kilowatt of.
to make 3 kilowatts.
Okay,
But from the demand perspective, the kilowatt hours I think is easy, but the demand is a little bit fuzzy. And realistically, I don't think that's the way that it would be, because the heat pump is going to run on and off, whereas the lighting is on all the time. And that's why I want to make sure it was clear, and I give you an approach to do that.
So wait, do you want us to take the difference between the lighting? Like if let's say we save 2 kilowatts from changing the lights, but we gain 1 kilowatt from the air conditioning. Do you want us to just do 1 kilowatt, or like, how do you know what I mean? Like take the difference between the lighting and the air conditioning.
Well, I'll bring it. I like my scenario because the numbers are easy, right? We save 3 kilowatts demand in lighting.
Yeah.
We save 3 kilowatts. The COP of our geothermal system is 3.
Right.
What is our additional demand from the heat pump?
1 kilowatt because it equals 3
Yeah.
kilowatts.
Exactly. Yep.
What,
No, go ahead,
I
Xavier.
know, what if I think, like, you get a same number, like, how do you say, if we save in 3 and then the COP is 3.
Okay, I would normally write this on the board, but I'm going to do it on the computer here to help maybe Eric out, or you guys can watch this as a reference. So let's say we saved, let's say we saved 5. Maybe I'll make a PowerPoint here. Maybe Excel would be the best way to go, actually. Microsoft Office, Excel. And I mean, this is just very similar to the document we did yesterday, right? But, so we're going to save, what do we want to save? 4.5 or 4.8 kilowatts. The COP of our system is what?
3.
2.8.
2.8. Okay, additional heat pump demand is going to be equal to some amount of kilowatts. What is the formula for that?
4.8 divided by 2.8.
Exactly. 4.8 divided by 2.8. So our additional heat pump demand then becomes 1.7.
Yeah, and that's just the way we're doing it for this.
Yeah,
It would probably be less than that.
it would probably be more
You think so?
because the light, like I said, the lights are on. They're pumping out 4.8 kilowatts
Yeah.
all the time. When our heat pump, if it was sized perfectly on the coldest day of the year, it would run nonstop. How am I going to say this? So the heat pump would be sized to meet, it needs to be a bit, okay, this runs 4.8 kilowatts all the time. If our heat pump did not run all the time, right, because it turns on, turns off, turns on, turns off. If it doesn't run at 4.8 kilowatts all the time, is it going to have to be bigger or smaller than 4.8 kilowatts? It's going to have to be bigger.
Shouldn't that be the new demand, not how much we saved?
That's what
No, because here we're talking about we've saved 4.8 kilowatts from retrofitting the lighting, so we're gonna have to put 4.8 kilowatts back into the system, and that's what we're doing with the heat pump.
So the total savings of kilowatts is actually like 3.1.
3.1?
Yeah, 4.8 minus 1.7.
Oh yeah. So that's if we go back to the back to here. So that's I've done supplemental heating, supplemental cooling, and then the final question is what is the overall savings?
Okay.
Okay.
Because the question's kind of weird because it says how much additional kilowatts will be required. Well, you're not really adding any kilowatts to the base case.
Okay. How much? I'll change it on here, and you can change it on yours. How much kilowatts and kilowatt hours be required to make up the additional heat required. That's better? Any questions on that? The heating part?
Probably on Sunday.
So it's just your kilowatt savings divided by the COP is what you need to make up for the lost heat.
Yeah. And you kind of missed the presentation yesterday, but some of these formulas and stuff are in this spreadsheet.
I mean, really, for the purpose of calculating, it would have been easier to not use a geothermal system.
I know. This is the final exam of commercial
but
energy
we're
auditing.
We're not even sure if that's accurate way of doing it.
It's accurate. It's just the demand. The kilowatt hours is very accurate. The demand, we probably need to actually record the demand from that.
Yeah, that's what I'm saying.
That's fine.
Another way to look at it is you almost need to measure it, right? Because the heat pump's already running with the lights on.
Mhm.
So, and this goes back to load inventory. What is the probability that that heat pump is going to contribute to the peak demand? And if we take the lights away, the probability is going to go up. But it's not actually going to be, the probability is going to go up. Probability, is that the right word?
Yeah. Yeah, that makes sense.
Uh,
The likeliness of it turning on.
But there's actually like a proper term for it's in the load inventory. The diversity factor. Right? The diversity factor for this heat pump would have been 60%. If we take some of the lighting away, the diversity factor is going to go up. Or we need to put even a bigger heat pump, which is essentially what I'm getting you folks to do now. Okay. That's the way we'll roll with it for now. Okay. The cooling, I think, is a bit okay. So supplemental cooling, when we install the lower wattage lights, we will have to provide less cooling from the geothermal system. The cooling system operates approximately blank months per year at a COP blank. What is the kilowatt and kilowatt hour savings from the reduction in cooling load?
Pretty straightforward.
Okay, and then the last one, what is the overall savings in dollars? So of course you use the numbers that you found in the number one.
And we need to know heating and cooling season.
Yeah, that's why the months is written on there.
Oh, okay, gotcha.
Yeah.
Great.
Okay. So question 2, the heat pump in room 223 provides air conditioning, and because it is sized properly, also dehumidification. Air enters the heat pump at blank degrees C and blank relative humidity. You can see condensation being removed via the condensate drain. The temperature leaving the heat pump is blank degrees C. A, what is the new percentage relative humidity? And B, that's the one I'm gonna strike through for now. And I wish we had more time, but I will definitely have an answer for you. I just am not going to test you on it. Okay, so any questions on that? Once we square away all the questions, then you will have your values in your blanks.
Hey, that little hair thing is on sale for $37 in the flyer. You know, that Con Air.
Con Air?
Yeah.
Oh, the
It
thing
went
for
on
your
sale.
head.
You go buy one?
I'm going to now.